You've probably heard the word entropy thrown around and just kind of nodded along, right? Thinking it means, what, disorder or messiness? Well, what if I told you it's actually about information? And not just any information, but specifically the information that we don't have. So today, let's dive in. We're going to crack the code on one of the most misunderstood and honestly most beautiful ideas in all of science.
Okay, so our story begins with a real head-scratcher, a mystery that stretches from the unbelievably huge to the unbelievably small.
Just try to wrap your head around this number. Well, it's basically impossible. This is the estimated entropy of all the supermassive black holes in our universe. And yeah, that's measured in bits. It represents a truly colossal amount of information that is totally and completely hidden from us, locked away forever.
Now let's slingshot all the way to the other end of the scale. This number, just about 23 bits, is the entropy that's been measured for a single molecule of hydrogen gas at room temperature. Now 23 seems tiny compared to the last number, I get it, but hang on. Think about what we're saying. That's for one single molecule. And right there, that is our mystery. How can one of the absolute simplest things in the entire universe, a single hydrogen molecule, contain so much missing information? It seems wild, right? Well, to find the answer, we have to completely reboot our whole understanding of what entropy even is.
All right, first things first. We need to just take that old fuzzy idea of disorder and just toss it out the window. Because the real key, the central insight, is that entropy isn't about how messy your room is. It's about your own ignorance.
This is the absolute core of it all. Entropy is a precise, you can put a number on it, measure of the information we are missing about a system. You know, stuff like the exact position, the exact speed of every single particle inside. It's a number that quantifies what we don't know.
Okay, so how in the world do you measure missing information? Well, it all starts with this simple, powerful little formula. And the idea is actually super intuitive. Think about it. When a really rare, super low probability event happens, you learn a ton. But if something totally common and expected happens, well, you didn't really learn much, did you? That's all this says. The minus sign is just there to make sure the number comes out positive.
Let's make this really concrete. A simple coin flip. Before it lands, you're in a state of maximum uncertainty, right? It's 50-50. The moment you see its heads, that uncertainty vanishes. You've just gained exactly one bit of information. That bit is the fundamental currency we're dealing with here.
But of course, most things in life aren't just one simple coin flip. Usually, there are lots of possible outcomes with different probabilities. So what we really want is the average amount of information we can expect to get. And that, my friends, is what Shannon entropy calculates. It's the expected surprise, averaged over all the possibilities. The more uncertain things are, the higher the entropy.
So if entropy is what we don't know, what do we do when we have some information, but not all of it? Like, what if we know the average energy of a gas, but nothing else? Well, how do you make your best, most honest guess? This leads to a really profound idea.
And this isn't some weird, newfangled concept. The great physicist and mathematician Laplace basically nailed it centuries ago. The principle we're about to talk about isn't some arbitrary physics rule. It's just common sense, written down in the language of math.
It's called the principle of maximum entropy. And the logic is it's beautiful. It goes like this. You start with the facts, the things you absolutely know to be true. Then you admit that there are still a whole bunch of ways things could be. So which possibility do you bet on? You choose the one that has the biggest entropy, the one that leaves you the most uncertain. Why? Because it's the most honest guess. You're not assuming any extra information that you don't actually have. You're maximizing your ignorance on purpose. And believe me, this isn't just a philosophical exercise. When you apply this principle of honesty to a physical system, like a box of gas where you know the average energy, bam! Out pops one of the absolute cornerstones of physics, the Boltzmann distribution. It's the formula that perfectly describes how energy is distributed in any system that's settled down into a stable temperature. Okay, so we have a guiding principle. Be honest about what you don't know. But how do we actually run the numbers? For that, we need a master tool, a kind of mathematical skeleton key that unlocks everything else.
So let me introduce you to the partition function. Physicists usually just call it Z, and it's so much more than just another equation. It's like the Rosetta Stone for this stuff. It's the central hub that contains basically all the information you could ever want about a system.
The power packed into this one function is just staggering.
At its heart, Z is basically a special way of counting all the possible states a system can be in, giving a little less weight to the really high-energy states that are harder to get to. And here's the magic. Once you've calculated Z, you can use it to derive almost everything else. The average energy, something called free energy, and yep, you guessed it, the entropy.
All right, time for a quick check-in. We know entropy is missing information. We have a principle of honesty to guide our guesses. And we have the mathematical tool, the partition function, to do the heavy lifting. We have everything we need. We are ready to go back and solve the mystery of those 23 bits.
But there is one final, absolutely critical piece to this puzzle. See, early calculations treated molecules like they were tiny, numbered billiard balls. If you have ball #1 here and ball #7 over there, that's one state. If you swap them, that's a new state. But what if? What if the particles are all fundamentally identical?
And that right there is the game-changing insight. Real hydrogen molecules are perfect clones of each other. They are completely indistinguishable. A situation with molecule A here and B there is the exact same situation as B here and A there. You can't tell the difference. And when you realize the old theory was overcounting the number of states by a massive, massive amount, and you correct for it, the whole formula changes. So, you take our modern understanding of entropy as missing information. You apply the principle of maximum entropy, use the power of the partition function, and you correctly account for the fact that all hydrogen molecules are identical. You put all that together and run the numbers, the theory predicts you should find about 22 bits of missing information per molecule.
So that's the theory. Then, you go into a laboratory and you actually measure it. And what does the experiment find? About 23 bits per molecule.
I mean, come on, that is an absolutely incredible agreement. It's a near perfect match, and it's the ultimate confirmation. Those 23 bits aren't some vague metaphor for disorder. It is a precise, physical accounting of our actual ignorance about the state of that single tiny indistinguishable molecule. We've cracked the code. And this all leaves us with a pretty fascinating, almost philosophical final thought. If one of the most fundamental laws of thermodynamics is actually, at its heart, a statement about the limits of our own knowledge, it really makes you wonder, doesn't it? What other cosmic mysteries, from the weirdness of the quantum world all the way up to those supermassive black holes we started with, are really just problems of information, waiting for us to figure out what it is we don't know?